Hello. This time I'm going to explain section 5.2 of the Pearson calculus, which is about the sigma notation. Sigma notation is something that is actually covered in algebra and pre-calculus, but let's review those stuffs by solving some basic questions. Okay, problem number 1. Write a sum without sigma notation. So what is sigma notation? So this is called sigma. K is 1 through 2 of 12k over k plus 2. So sigma notation is, for example, when you have k is equal to 4 through 7 of some function in terms of k. This means you are going to find the function value when k is equal to 4 and 5 and 6 and 7. Okay, so this means you are going to take a sum of the y value for the function between k is equal to 4 and 7. So f of 4 plus f of 5 plus f of 6 plus f of 7. Okay, so that's how the sigma works. So in this case, you are going to evaluate this function value when k is equal to 1 and for when k is equal to 2. So the first question is write the sum without some sigma notation. Do not simplify, do not evaluate. So I just merely simply just plug in k is equal to 1 here. So when k is equal to 1, it's going to be 12 times 1 divided by 1 plus 2. So that's the first term. Second term is when k is equal to 2. Okay, so that's the last one. So it's going to be 12 times 2 divided by 2 plus 2. So if we rewrite this expression without sigma notation, it's going to be like this. Okay, now just do evaluation. So just compute 12 over 3 and 24 over 4, which is 4 plus 6, and that is 10. Okay. Let's go more. Number 2. Same problem with different notation, different function. So sigma is equal to k 4 through 8 of cosine k pi. So we are going to evaluate this function for k is equal to 4, 5, 6, 7, and 8. So when k is equal to 4, it is cosine 4 pi. When k is equal to 5, it's 5 pi, and 6 pi, 7 pi, and 8 pi. Okay. So that's the first part. Now we are going to evaluate it. So cosine of 4 pi. So thinking about the unit circle, starting with here. So 2 pi is 1 revolution. 4 pi is 2 revolutions. So 4 pi is here. So cosine of 4 pi is equal to 1. 5 pi will be here. You have half revolution more. So it's going to be -1. And 6 pi, it's going to be +1 again. 7 pi, -1. And 8 pi, +1. So that sum is going to be equal to 1. Next one, bit difficult one. Which of the following expresses 1 plus 5 plus in sigma notation? So this is actually 1 plus 5 plus 5 squared plus 5 cubed, 5 to the 4th, 5 to the 5th, and 5 to the 6th. Okay, so we are going to rewrite this one with sigma. Well, there are 7 terms, and one natural choice will be, well, this is same thing as 5 to 1, and this is same as 5 to 0. So natural choice would be, we have a bunch of 5 to the power of k, where k is starting from 0 and up to 6. So the choice B seems to be expressing this one correctly. But sometimes, well, it's always possible that you can express this one in slightly different form. For example, if you want to start with k is equal to 1 as a first term, second term, third term, fourth term, fifth, sixth, and seventh, then you should have 7 terms, so 1 through 7. And for the first term, it's 5 raised to the power of 0. Second term is 5 raised to the power of 1, and so on. So you can rewrite this one as 5 to the power of k minus 1. So you subtract 1. So when k is equal to 1, it's 0. K is 2, it's going to be 1. K is 3, it's going to be 2. And k is equal to 7 gives you 5 to the power of 6. So this is actually same expression. I mean, same thing in slightly different way of expressing it. Okay. The another one is probably the same. It's a weird. It's kind of hard to come up with this notation, but let's see what this really means. Okay, so let's see, this is the same thing. So this is starting with k is equal to minus 1, so it's going to be 5, 0. When k is equal to 0, it's 5, 1. And k is equal to 2. When k is equal to 1, it's going to be 2. And and the last one going to be 5 to the power of 6. So the choice C also showing the same thing in different style. So all 3 of them in this case shows the same expression. So the answer is, I just click everything. Okay, so okay. So next one is, which formula is not equivalent to the other 2? So this means of these 3 expressions, 2 of them is the same, third another one is different. So let's see. So first one, k is equal to 10 through 12 of negative 1 to the power of k minus 9 over k minus 9. So when k is equal to 10, it's going to be 1 and negative 1. When k is 11, it's going to be 2 and 1. And when k is 12, it's going to be 1/3 negative. Look at the choice B. This is k 0 through 2, negative 1 to the power of k, k plus 1. So negative 1 raised to the power of 0 is positive 1, and bottom is 1. And when k is equal to 1, it's going to be negative 1 over 2. And when k is 2, it's going to be positive 1 over 3. So similar, but they are different. So let's see which side C is. It's starting from negative 9 to negative 9 to negative 7. So when k is negative 9, it's going to be 1 on the bottom and top going to be, because it's odd power, so negative 1 raised to the odd power, it's going to be negative 1. And next item is negative, you plug in negative 8, you're going to get, because it's an even power, it's going to be positive 1. And the third one going to be negative 1/3. So A and C are equivalent and B is not. So the choice is the B, which is the top one in this case. Okay, number 5. Express the following sum in sigma notation. Use 1 as a lower limit of summation and k for the index of summation. So I have to use the index as k, and I have to start from 1. Well, this clearly has 24 different terms. So I should have 1 through 24. And the first term is 1, second term is 2, third term is 3, and so on. So k's term should be equal to k. So all we need to do is like this, okay? First term is 1, second term is 2, third term is 3, and so on. So k's term should be equal to k. So the simple function we should come up with first term 1, second term 2, third term 3. So if this is a pattern, the k's term would be k. That's what is going on here. Okay, next one, number 6, similar question. Again, I have to use a k as the index of summation, and I have to start from 1. So there are only 4 terms. So I should have k is equal to 1 through 4. Now the first term is 1, second term is 4, which is 2 square. F3, third term is 9, which is 3 square. And the fourth term is 16, which is 4 square. So in general, k's term is k squared. So it's gonna be like this. Okay, and again, this question is rewrite the expression in sigma notation. So now you have 3 over 2 plus 3 over 4 plus 3 over 8 plus 3 over 16. So you have 4 terms, so I have to start from k is equal to 1. So there's 4 terms, so 1, 2, 3, 4. I should end up for 4. Now looking each fraction is kind of hard to see, but this is actually a geometric series. But the numerators remains 3. So you see, first term is 3 over something, second term is 3 over something, and so on. So the k's term would be 3 over something. Now bottom is 2, 4, 8, 16. It is a geometric sum, geometric sequence. It can be described as 2 to the power of 1, 2 to the power of 2, and so on. So it's going to be k's term going to be 3 over 2 to the power of k. Okay, so you want to add up these terms. Okay, you can check by plugging k is equal to 1, k is equal to 2, k equal to 3, and so on. Okay, so make sure to test your answer is actually express the same thing as the original summation. The next one is very simple too. I'm not going to explain this one now. Okay. Okay, now you have to do the sum. This is actually, you can do it by hand, but you can apply the formula as well. So I'm going to introduce you the formula. This means 1 plus 2 plus 3 plus 4 plus up to n, which is first sum of the first n natural numbers. And the formula for this one is actually you can derive it from formula for the sum of the arithmetic sequence. So it's going to be n times n plus 1 divided by 2. When you have the sum of the squares of the first n integers, that is actually, it's not easy to derive it, but it's going to be 6 and n plus 1. And you multiply it by the sum of the first 2 terms here, which is 2n plus 1. Okay. And you have to memorize it for the third one, the cubic one. It's going to be the sum of the cubes of the first n terms, n numbers. And this is actually equal to n square, n plus 1 square divided by 4, which is actually equal to the sum of the first n integers squared as well. So using those formulas, applying those formulas for part A, so this is 1 plus 2 plus 3 plus up to 13. Okay, 1 plus 2 plus, you don't have to write down this, but up to 13 is same thing as 13 times 14 divided by 2, and that is equal to 91. Part B. So 1 square plus 2 square plus 13 square. That can be found by 6. 13 times 14 times the sum of those two numbers, which is 27. This is not easy to do it, so simplify this, it's going to be 819. Now the third one, sum of the cubes, is same thing as, let's use this one because we already found this. Oops. 13 times 14 divided by 2 square. So that is equal to 91 square, and that's going to be 8281. Okay. So it's just like a practicing applying those formulas. Okay, now next one is quite simple because you only have 6 terms. So you can do it by just simply adding those terms. But if you apply some properties of the sigma, you can apply the formula we just used once in the previous question. So the one of the property of the sigma is when you have some constant number multiplied by some function, this constant number could be put outside of the sigma notation. And it is true because this means a times f1 plus a times f2 plus a times f3 and so on, which is same thing as a times the sum of f1, f2, f3 and so on. So you can put a outside and use a sigma notation for this part. Applying this, so you can put -7 out. And you can use the sum formula here. Or you can just do 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay. So I'm going to use a formula here. It's going to be 6 times 7 divided by 2. So the answer is -147. Okay. Okay, now we are going to apply the sigma notation to the current integration area problems. Okay, graph the function fx is equal to x squared minus 1 over the interval of 0 through 2. So this is a parabola, concave upward parabola. It's 1 here, and let's say this is 2. So it's gonna be, here's 1, here's -1, 2, 3. So the x-intercept is 1, and here's a vertex. So the parabola looks like this. Okay, partition the interval into 4 subintervals of equal length. So we're gonna split the interval 0 through 2 into 4 intervals. 0 through 1/2, 1/2 through 1, 1 through 1.5, and 1.5 to 2. Okay, remember that we are using this notation to find the common width. Okay, so in this case, 2 minus 0 for the total length divided by number of intervals to get 1/2. So each length is 1/2. Now you then add your sketch the rectangles associated with the Riemann sum. So k is 1 through 4 of f of ck delta xk. Okay, so delta xk is basically the length of each rectangle, horizontal length of the rectangle, and this is the height. Now, in part A, you are going to use the left-hand endpoint. Okay, so I'm gonna use this height for the first interval and this height for the second interval, and this one for the third interval, which is 0, and this one for the fourth interval. So graph looks like a negative rectangle, nothing, and the right positive rectangle. The only choice with that is choice A here, okay? Now, we do the same thing for the right-hand case. So it's 0 here. So if we do the right hand, we're gonna use the right end to get the first rectangle. Second rectangle has a 0 height, and the third rectangle is this, and the fourth rectangle is using right end. You're gonna get this. So negative, nothing, positive, big positive. So choice B, the problem for B is negative, 0, positive, positive is only choice A. So A is the correct one. Okay. Midpoint is a bit harder. Midpoint is a bit harder. Okay, so the midpoint case. So here is 2. So midpoint is I have to take a midpoint. So midpoint in each interval. So it's somewhere here, somewhere here, somewhere here, and somewhere here. So graphically, you have 2 negatives and 2 positives. And the only choice with that gonna be choice B here. So B is the best choice for us in this case. Okay, this is the same problem with just a cosine between negative pi through pi. So let's do this one. It's basically same problem. So the cosine function, y is equal to cosine has a y-intercept of 1. And at pi, it's going to be negative 1. And at negative pi, it's going to be negative 1 as well. And it has a 1 period in this interval. And here it's at pi over 2. Now, I had to add the rectangles associated with a Riemann sum of 4 intervals where CK is the right endpoint. So I have to use the right endpoint. So for the first interval, I have to use the right endpoint. So I have to use this one. So there's no height. On the second interval, the right end is this height. So I'm going to get a big horizontal, big vertical length here. Third one, 0 again. And fourth one, it's going to be negative. So nothing, positive rectangle, nothing, negative rectangle. Okay, so the best choice will be choice B. Okay, now new terminology. You don't have to memorize this one, but just know what it is for solving this problem. So what is a norm? Norm of the partition, P. And P is like 0.2, 0.6, 0.8, 1.1 to 2.7. So this is basically you are splitting the interval starting with 0.2 and 2.7. Okay, in here you want to have 0.6, 0.8, 1.1, 2, and 2.7. Okay, the norm for the partition is basically the maximum distance of 2 consecutive points. So you are checking the distance here, distance here, distance here, distance here, and distance here. And you want to pick the largest distance you have. So, well, my picture is not good. So this distance looks like the largest, but let's check it. So between 2.2 and 0.6 is 0.4. 0.6 to 0.8 is 0.2, and here's 0.3, and here's 0.9. Okay, so the 0.9 gonna be the norm for this partition. Okay, so that's the largest horizontal distance between two consecutive points. Okay, same problem here. So let's draw it neater this time. So let's say this is 0, and here's -2, and here's +2. So 1.6 is around here. 0.5 is around here. 0.1 is here. 0.1 is here. 0.4 and 1.1. We are not going to count this. So this distance is 1.1, which is long. Next one is 0.4. Next one is 0.2, 0.3, and 0.7. So this is the largest. So that's going to be the norm for this partition. Okay, the last three problem of this section is a bit harder. So number 15. So for the function given below, which is f of x is equal to 4x, find the formula for the Riemann sum obtained by dividing the interval into n equal subintervals and using the right-hand endpoint for each ck, then take limit. Okay, so you have a function like this. Let's say you have a function fx. In this case, it's 4x. And you have an interval of 0 through 3. You are going to divide this one into n subintervals. So n subintervals, okay? And you're gonna evaluate you're gonna make a rectangle with using a right point estimation. Okay, so you're gonna do something like this. In the previous section, we did this one for 2 intervals or 4 intervals, but here you have to use an n interval. So number of interval is n. Left endpoint is 0, right endpoint is 3. So when you divide this interval into n equal subintervals, each distance, each width gonna be 3 over n. So each length is 3 over n. So first number is 0, and the second number here gonna be 3 over n. Next number is another 3 over n, so it's gonna be 6 over n. Another number here is 9 over n, and so on. So in general, 0 through 3 is divided into 3 over n, 3 times 2 over n, 3 times 3 over n. So the case term gonna be 3 times k over n, and so on. Okay, so that's gonna be important. Now, let's try to estimate. Well, let's try to find the sum of the n rectangle areas. So that is called Sn. So the common width, common horizontal length is 3 over n. That's a horizontal distance. Okay, that's a horizontal distance. That's this part. Each rectangle has the same horizontal length. So that's this one. Now multiply it by height. And height gonna be, because you are using the right points, the first one gonna be the function value at 3 over n. Second term gonna be 6 over n. And third term gonna be f at the 9 over n. And so on for n terms. So using a sigma notation, it's gonna be 3 over n sigma f of 3 times k over n. Okay, this is for k equal to 1. This is for k is equal to 2, and so on. How many times you had to do? Well, k starting from 1, and because there are n intervals, you're gonna get 1 through n. Okay, so I wrote, I made a mistake in this problem after 3 tries. It's because I didn't know what the problem is asking for. It seems like a problem is asking to simplify it as much as possible. So I had to remove this. I mean, I have to evaluate this sigma notation. Okay, so in this case, the function we have is fx is equal to 4x. So this is going to be 4 times whatever the input is. So that is equal to 3 over n sigma k is 1 through n of 12k over n. Okay. Now, how do we find the sum? Well, if you notice that this is similar to like negative k, 7k in the previous problem, like this number could be put outside of the sigma notation. The same thing could be said here. So k is a variable inside the sigma notation, but this part is the same. So you can put out 12 over n outside of the sigma notation like this. Does that make sense? Well, if you rewrite this one without the sigma, it's clear that when k is equal to 1, it's going to be 12 over n. When k is equal to 2, it's going to be 24 over n. When k is equal to 3, it's going to be 36 over n, and so on. You see that all of them is multiple of 12 over n. So you can factor out to see much simpler notation, sum notation here. So this is basically 1 plus 2 plus 3 plus 4 plus up to n, which is using the formula, it is n times n plus 1 divided by 2. You can reduce this fraction because this is in factored form. So let's divide top and bottom by reducing some fractions. It's going to be 18 n plus 1 over n after reducing the fraction. So that's going to be the simple form of the area of n rectangles. Okay. Now we are going to take a limit. By increasing the number of intervals into infinity, you can find a great estimation to the area under the curve. So to find the area under the curve, let's say that is equal to S, you want to take a limit of the approximation, the sum of the n rectangles, and n make it to infinity. So I have to take a limit of 18 times n plus 1 divided by n. You can expand the fractions, expand the numerator if you want, if that makes it simpler, but they're not necessary. So the first thing to do is Torima Dainu. So when you just plug in n, go to infinity, the denominator is infinity and numerator is infinity. So this is indeterminate form of infinity over infinity. So things to do is you divide both sides, top and bottom, by the largest factor in the denominator, which is n to the power of 1. So divide top and bottom by n. The bottom become 1 and top become 18 times divided by n, 1 plus 1 over n. Now you can take a limit again. It's going to be 18 plus 0, so it's going to be 18. Okay. So the limit is 18. By the way, this is not really a curve, but it's just like a, y is equal to 4x. It's just a straight line. So it is a right triangle. And when x is equal to 3, the height is 12. So you are basically finding the area of this right triangle with base is 3 and height is 12. So you see that the result agree with the area formula for the area of the triangle. Okay, now it's the same problem, but with different function. So idea will be very similar. Okay, so now you have a quadratic function with interval 0 through 1. you divide this one into n subintervals. So each point is like, first point is 1 over n, second point is 2 over n, 3 over n, and k over n in this case. So Sn gonna be the common horizontal length. Common horizontal length is b minus a over n. So 1 minus 0 over n. So it's 1 over n. Now the height is, you want to add n rectangles, and each area, each height is going to be f of k over n. Okay, first one is a height at 1 over n. Second one is a height at 2 over n, and case one going to be k over n, and so on. So that's a situation. So I just need to simplify this. So in this case, fx is equal to 3x squared. So 3 times input square. 3 times input square. Just like a previous question, we can move the constant outside of the sigma notation. So k, you cannot move it, but n squared and 3 can be. So it's going to be 3n cubed outside, and you just have a sum of the first n squares. Using the formula, this is becoming 6n, n plus 1, and 2n plus 1. Okay, so that's reduced to, you reduce this one and reduce this one, you get 2n squared, n plus 1, and 2n plus 1. Okay, we can simplify this one a little bit for the limit process. Let's expand the numerator like this. And because the denominator is a monomial, you can split into 3 fractions like this. And that might make us a bit easier to find the limit. Okay, so this is equal to 1 plus 3 over 2n plus 1 over 2n squared. So that's Sn. Okay, now it's easy to take a limit, makes a number of rectangles to the infinity. So you just plug in, you see it's going to be 1 plus 3 over infinity, which is 0, plus 1 over infinity, which is 0. So the limit area is equal to 1. Okay, now it comes with a cubic function with a terrible negative interpretation, negative interval here, but the idea is the same. So I'm going to quickly write down the solution here without much explanations. So you have some function, that function has positive values. It's a decreasing function, but who cares? -1 through 0. So divide this one into n intervals. So n intervals. The left end is -1, right end is 0. So the common width is going to be b minus a divided by n. So it's going to be common length is 1 over n. So that's the horizontal length here. Okay. Now each term is going to be a bit harder because you start with -1. So you add 1 over k to -1. So here's a partition. So first number is this, not 0. We are starting with something else. That's so after you add 1 over n, you're gonna get -1 plus 1 over n. And the second number is -1 plus 2 over n, and so on. So basically, you have like n numbers here, and each term looks like -1 plus k over n. Okay. So yeah, so be careful that you start with -1 in this case. So now find the rectangles. So rectangle has a horizontal width of 1 over n. You have n rectangles, k is 1 through n. And each rectangle has a height of the f values at these numbers. So it's f1 of -1 plus k over n. Now, f is a bit complicated. And that's terrible. 22 times input square plus 22 times input cube. You can put 22 out quickly, but others I had to expand a little bit. So expand this one, it's going to be 1 minus 2k over n plus k square n square. I really need a larger space here. And when you expand this one, it's going to be cube minus 3k square n square plus 3k over n minus 1. Okay. Let's combine like terms. So this is only cubic term. Here's a quadratic term. And here's a linear term. And the constant term will be disappeared. Okay, now I have to use a formula to find the sigma of k cube, k square, and k. Let's factor out. Well, just forget about this one. Let's just use a formula for this one and this one and this one quickly. So it's going to be n cubed stays here. And the formula for the sum of the cubics is going to be not n square. 4 on the bottom, that's a formula. N square, n plus 1 square. Okay. For the sum sigma of the k square, going to be 6 n plus 1 to n plus 1. Oh, I need more space. I really need more space. Okay. And thirdly, this one, sum of the linear term, 1 plus 2 plus 3 plus is 2 and n plus 1. Okay. Now we can simplify a little bit. This n square is canceled, so it's going to be 4n n plus 1 square. And second term, you can reduce 3n. So it's going to 2n. You can factor out 2n. So you're going to get 3n here and n plus 1 and 2n plus 1. And this one, you can reduce n. So you get 2 here and n plus 1 here. Okay. Now, let's factor out n plus 1. This is a common term here. So you can factor out n plus 1 out. And let's make the denominator the same after that. So the least common multiple of the denominator is going to be 12n. So after you factor out this one, you have to multiply it by 3. Second term, after you remove this one, you multiply it by 4. So it's going to be 4. And this one, you have to multiply top and bottom by 6n after you move this one. So it's going to be 6n. So simplify the numerator. We finally get something simple enough. That's going to be 6, 3, 9. It's going to be n. 3 minus 4, it's going to be minus 1. So it's going to be n minus 1. So it looks good. Yeah. that's gonna be 6n squared, 11n squared minus 1. Or you can rewrite it as 11 over 6 minus 11 over 6 minus 11 over 6n squared. So that's the simplest form. Okay, that's Sn. Now finding a limit is simple. Find the limit is simple. So you just take a limit of this one, and if you did the simplification, then limit is 11 over 6 minus 0, 11 over infinity is 0. So you get 11 over 6 instantly. Okay, so that's gonna be the area under the curve. That's conclude this section. Okay. So mostly review of the sigma notation, but the last three problem is application of that to the Riemann sum, and that's what you want to be able to compute comfortably. Thank you very much. Okay.